Right now, somewhere in the Milky Way, a star that has been burning for 10 million years is about to die in the time it takes you to finish a cup of coffee. Not 10 million years from now, not 1,000, not even tomorrow. Somewhere in this galaxy, at this moment, a stellar core is ticking toward a threshold it cannot come back from. And when it crosses that line, everything that follows will happen so fast that the star's own surface will not know it is dead until hours after the event is over. This is a story about 10 minutes. 10 minutes that undo 10 million years of construction. 10 minutes that begin in silence and end in the most violent explosion the universe regularly produces. 10 minutes that forge the elements your body is made of and scatter them across light years of empty space. But to feel the weight of those 10 minutes, you need to understand what came before and just how much is about to be lost. The star we are talking about is not like our sun. Our sun is modest, middle-aged, burning its hydrogen at a pace that will sustain it for another 5 billion years. The star in this story is something else entirely. It is 15 to 20 times more massive, hundreds of thousands of times more luminous, and so physically large that if you placed it where the sun is, its outer atmosphere would swallow Mercury, Venus, Earth, and reach past the orbit of Mars. If our sun is a campfire, this star is a furnace the size of a city block, and it has been burning through its fuel at a rate that would horrify an accountant. For most of its life, this star converted hydrogen into helium in its core, just as the sun does. But because it is so much more massive, the pressures and temperatures at its center are ferocious, and the hydrogen ran out in a fraction of the time it takes the sun. Where the sun will burn hydrogen for 10 billion years, this star exhausted its supply in roughly 10 million, 1,000 times faster. And when the hydrogen was gone, the star did not stop. It contracted, heated up, and began burning the helium ash into carbon and oxygen. When the helium was spent, it burned carbon, then neon, then oxygen, then silicon. Each new fuel burned faster than the one before because each required higher temperatures and produced less energy per reaction. The star was climbing a staircase where every step was shorter and steeper than the last. Hydrogen sustained it for 10 million years, helium for about 1 million. Carbon lasted roughly 1,000 years, oxygen barely a year, and silicon, the last nuclear fuel the star will ever ignite, burns for approximately 1 week. 1 week. After 10 million years of life, the final act of nuclear fusion lasts 7 days. And at the end of that week, sitting at the very center of the star, there is a ball of iron roughly the size of the Earth and 1.5 times the mass of the Sun. Iron, the element with the highest binding energy per nucleon, the most stable arrangement of protons and neutrons that nature permits. You cannot extract energy by fusing iron into heavier elements. You cannot extract energy by splitting it into lighter ones. Iron is the end of the nuclear road, the bottom of the valley, the place where the physics of fusion simply stops. The star does not know this, of course. Stars do not know anything. But if you could somehow stand at the boundary of that iron core and look inward, you would be looking at a death sentence written in the language of nuclear physics. No force the star can generate will prevent what happens next. And what happens next takes less time than you have spent listening to this paragraph. There is something quietly staggering about this asymmetry. A star lives for 10 million years and dies in 10 minutes. The ratio is almost incomprehensible if you scaled the star's entire life down to a single calendar year, January 1st to December 31st. The 10 minutes of its death would occupy the last 4,000ths of a second before midnight. Less than the blink of an eye, less than the time it takes a hummingbird's wing to complete a single stroke. And yet those 4,000ths of a second will release more energy than the star produced in all the months that came before them combined. This is what we are going to follow tonight. Not the broad arc of a stellar lifetime, but the final moments, second by second, in some places millisecond by millisecond, when a structure that took millions of years to build tears itself apart and, in doing so, seeds the galaxy with the raw material for new stars, new planets, and, eventually, improbably, new life. You are made of this violence. The calcium in your bones was assembled in a core like the one we are about to enter. The iron in your blood was forged in a furnace that collapsed under its own weight. The oxygen filling your lungs right now was scattered into space by a shock wave that for a terrible fraction of a second almost failed to launch. If that shock wave had stalled permanently, if the physics had gone a slightly different way, those atoms would have fallen into a black hole and you would not exist. That is the story we are telling. Not just the death of a star, but the birth of everything that comes after. But before we step inside this dying star and follow its final minutes second by second, I want to ask you something. If you have found your way to this channel, if the idea of listening to the inner mechanics of a stellar collapse while the night settles around you sounds like exactly the right way to end your day, then you are the kind of person Pale Light was made for. Consider subscribing if you have not already. Leave a comment and tell me where you are listening from tonight, what time it is where you are, and what brought you here. I read everyone. Now, let us begin. To understand what happens in those last 10 minutes, we first need to understand what the star has built over the course of its life, layer by layer, element by element, and why all of it is about to become a trap. A massive star does not simply burn, it builds. Over the course of its life, layer by layer, it constructs something that looks remarkably like an onion. Concentric shells of progressively heavier elements, each one nested inside the last, each one the spent fuel of a furnace that once roared at its center and has since moved deeper. The outermost shell is hydrogen, the lightest and most abundant element in the universe, the fuel that powered the star for the vast majority of its existence. Beneath that sits a shell of helium, hydrogen's ash. Beneath the helium, carbon, then neon, then oxygen, then silicon, and at the very center, a dense, hot, quietly growing ball of iron. This is not a metaphor. If you could slice the star open like a piece of fruit, you would see these layers as distinctly as the rings of a tree, though here, instead of recording years of rainfall and drought, each ring records a different epoch of nuclear fire. The hydrogen shell remembers the star's long, stable youth. The helium shell marks the beginning of middle age. The carbon and oxygen layers belong to a period of rapid change, when the core contracted and heated again and again, igniting each new fuel in turn. And the silicon shell, thin, searingly hot, still actively burning, is the star's present tense, the final chapter being written in real time. For most of human history, this layered structure was purely theoretical. We knew it had to be there because the physics of nuclear fusion demands it. Lighter elements burn at lower temperatures near the surface. Heavier elements require the crushing pressures found only deep inside. But no one had ever seen it directly, because massive stars do not generally peel themselves open for our inspection. That changed in the summer of 2025. A team of astronomers led by Steve Schulze, working with data from the Zwicky Transient Facility, announced the discovery of a supernova unlike any previously recorded. The object, designated SN 2021-YFJ, was located 2.2 billion light-years away, and its spectrum was extraordinary. Instead of the hydrogen and helium signatures that typically dominate a supernova's light, this explosion was rich in silicon, sulfur, and argon. The star had somehow been stripped of its outer layers before it exploded, exposing the deep interior that no telescope had ever observed in a dying star. It was, as the researchers described it, a star stripped to the bone. For the first time, astronomers were looking directly at the onion's inner rings, and the theoretical architecture held up precisely. But the architecture has a flaw, or rather, it has a consequence that the star cannot escape. Each shell burns for a shorter time than the one above it. Hydrogen sustained the star for roughly 10 million years. Helium burned for about 1 million. Carbon lasted perhaps 1,000 years. Neon, a handful of months. Oxygen, approximately 1 year. And silicon, the innermost burning shell, the last fuel the star possesses, will be exhausted in a matter of days. The reason for this acceleration is deceptively simple. As you climb the periodic table from hydrogen toward iron, each successive fusion reaction yields less energy than the one before it. Fusing 4 hydrogen nuclei into helium releases a generous 26.7 million electron volts. Fusing carbon nuclei together returns a fraction of that. By the time you reach silicon, the energy payoff per reaction has dropped so steeply that the star must burn its fuel at a furious rate just to maintain the pressure it needs to hold itself up against gravity. It is like an engine running on fumes. The pedal is flawed, the fuel gauge is falling, and the car is still slowing down. There is another cost that compounds the problem. From carbon burning onward, the core becomes so hot that it produces enormous quantities of neutrinos, subatomic particles so weakly interacting that they pass straight through the body of the star and escape into space, carrying energy with them. The star cannot reclaim this energy. It is simply gone. So the core must burn even faster to replace what the neutrinos have stolen, which produces more neutrinos, which steal more energy, which demands still faster burning. It is a feedback loop with no off switch, and it is driving the star toward its end at an accelerating pace. Every atom of calcium in your bones was once part of an oxygen-burning shell, exactly like this one. Every atom of iron in your blood was forged in a silicon furnace, no different from the one that is, at this moment, feeding the last few hours of this star's life. You carry the remnants of ancient stellar architecture in your body, layers that were assembled over millions of years, and then, in an event we have not yet reached in this story, torn apart in seconds. The outermost layers of the star are oblivious to all of this. The surface, a vast, cool, red expanse larger than the orbit of Mars, responds only to the slow rhythms of radiation pressure from below. It does not know that the core has cycled through 6 different nuclear fuels. It does not know that the silicon is nearly exhausted. It does not know that, deep inside, a ball of iron the size of the Earth is growing heavier by the minute. The photosphere drifts and pulses gently, as it has done for thousands of years, utterly unaware that the structure supporting it is about to fail. Because that is what the onion really is when you look at it with the right eyes. It is not just a record of the star's past, it is a countdown, each shell thinner and shorter lived than the last, each one bringing the star closer to the moment when the innermost furnace produces something it cannot burn, cannot break apart, cannot use, something that simply accumulates, growing heavier and heavier, until it crosses a threshold that no stellar process can reverse. The silicon is building that something right now, and what it is building, quietly, relentlessly, in the deepest interior of the star, is a trap. The trap is iron, and the mechanism that builds it is unlike anything the star has done before. Silicon burning, the process that fills the star's core with iron, is not really fusion in the way we usually think of it. When hydrogen fuses into helium or carbon fuses into oxygen, the reaction is relatively straightforward. Lighter nuclei collide and stick together, releasing energy. Silicon burning is stranger than that. At 3.5 billion degrees, the radiation inside the core is so intense that photons carry enough energy to smash silicon nuclei apart almost as fast as they are assembled. What actually happens is a frantic, two-directional process. Gamma rays shatter silicon nuclei into smaller fragments, helium nuclei mostly, and those fragments immediately recombine with other silicon nuclei, ratcheting the average atomic weight upward one step at a time. Destroy and rebuild, destroy and rebuild, over and over, billions of times per second, until the nuclei reach the most stable configuration available to them. Iron and its neighbors in the periodic table, nickel and cobalt and chromium. The whole process is less like construction and more like erosion, a river carving a valley not by adding material, but by tearing it away and letting it settle wherever the physics demands. The result is nickel-56, a radioactive isotope that will eventually decay into iron-56. But that decay takes days, and this star does not have days. In the core, the distinction between nickel-56 and iron-56 is academic. What matters is that both sit at the bottom of the binding energy curve, the lowest point on the graph that governs all of nuclear physics. You cannot roll downhill from the bottom of a valley. You cannot extract energy by fusing iron, and you cannot extract energy by splitting it. The star has reached the end of its fuel supply, and the product of its last reaction is the one substance in the universe that is perfectly, catastrophically useless to it. Meanwhile, something important is happening to the core itself. While the silicon shell burns, it deposits its iron ash onto the surface of the core like snow accumulating on a roof. The core grows heavier minute by minute, and the pressure at its center mounts. Electron degeneracy pressure, the quantum mechanical resistance of electrons to being squeezed into the same space, is the only thing preventing the core from collapsing. This is the same force that holds up white dwarf stars, the dense remnants of smaller suns that have long since exhausted their fuel. In a white dwarf, electron degeneracy is enough. The star is dead but stable, and it can sit in that state for billions of years, slowly cooling into darkness. But this core is not a white dwarf. It is hotter, denser, and, critically, still growing. The silicon shell is still feeding it, still adding iron to its mass. And there is a limit to how much weight electron degeneracy pressure can support. That limit was calculated in 1930 by a 19-year-old physics student named Subrahmanyan Chandrasekhar, working alone on a steamship crossing the Indian Ocean from Madras to Southampton. Using the tools of special relativity and quantum mechanics, both still young fields at the time, Chandrasekhar showed that no object supported by electron degeneracy pressure can exceed approximately 1.4 solar masses. Beyond that threshold, gravity wins. The electrons cannot push back hard enough. The object must collapse. Chandrasekhar could not have known at 19 that he was writing the death certificate for every massive star in the universe. But that is exactly what he did. The number he calculated, 1.4 solar masses, now called the Chandrasekhar limit, is the line this iron core is approaching. The silicon shell is still burning, still adding material, and the core is growing toward that line at a rate that can be measured in hours. The precise value of the limit is not fixed. It depends on the temperature of the core, on the ratio of protons to neutrons, on the electron fraction, and the entropy of the material. In a real star, the effective Chandrasekhar mass can range from about 1.34 solar masses to as high as 1.8, depending on conditions. But the principle is absolute. There exists a maximum mass, and the core is approaching it, and nothing the star does can change what happens when it arrives. Two processes are already conspiring to hasten the crossing. Deep inside the core, where temperatures exceed 10 billion degrees, gamma-ray photons have begun to shatter iron nuclei back into helium nuclei and free particles. This is photodisintegration, the same process that drives silicon burning, but now turned against the finished product. Each time a photon destroys an iron nucleus, it absorbs energy from the core. The core cools slightly. The pressure drops. The core contracts a fraction further, which raises the temperature and density, which triggers more photodisintegration, which absorbs more energy. It is a serpent eating its own tail. At the same time, the rising density is forcing electrons into atomic nuclei. At normal densities, electrons orbit their nuclei at a comfortable distance. But at 1 billion grams per cubic centimeter, the electrons are squeezed so tightly that their quantum energy exceeds the threshold for inverse beta decay. They merge with protons and become neutrons, releasing neutrinos in the process. This is electron capture, sometimes called neutronization, and it is devastating. Every electron that disappears into a nucleus is one fewer electron contributing to the degeneracy pressure that holds the core up. The floor is dissolving beneath the star's feet. Photodisintegration steals energy. Electron capture steals pressure. Both processes accelerate as the core contracts, and both feed back on themselves. The star has entered a spiral it cannot escape, a narrowing gyre of rising density and falling support, and the outcome is as certain as gravity itself. Somewhere in the next few hours, perhaps sooner, perhaps in a matter of minutes, the iron core will cross the Chandrasekhar limit. The electrons that have supported it for days will no longer be sufficient, and when that moment arrives, the core will not contract gently. It will not settle into a new equilibrium. It will fall inward upon itself at 1/4 of the speed of light, and everything above it will follow. The silicon clock has nearly run out. The last grains are falling. And deep inside a star that looks, from the outside, exactly the same as it did yesterday, the fastest catastrophe in the known universe is about to begin. The iron core crosses the Chandrasekhar limit, and the collapse begins without warning. There is no shudder, no sound, no flash of light. The electrons that held the core in equilibrium for days simply cannot push back hard enough against the weight above them, and in the space between one moment and the next, the core begins to fall inward upon itself. The transition from stability to catastrophe is not gradual, it is a cliff edge. One moment the core is a dense, hot, slowly growing sphere of iron. The next, it is in freefall. What happens over the following 10 milliseconds is the fastest large-scale gravitational event in the known universe. The inner portion of the core, roughly the innermost 0.7 solar masses, collapses homologously, meaning it falls inward as a single unit, every part of it accelerating together, maintaining its internal structure even as the whole thing shrinks. The outer core is different. It falls faster because gravity is pulling it toward the rapidly compressing center, and it falls chaotically, raining down on the collapsing inner core like an avalanche following the mountain it is stripping bare. The velocity of this infalling material reaches 70,000 kilometers per second. That is 23% of the speed of light. Nothing of this size anywhere in the universe has ever been observed to move this fast. To put that speed in human terms, at 70,000 kilometers per second, you could cross the distance from the Earth to the Moon in 5.5 seconds. You could reach the Sun in 36 minutes. You could travel from London to Sydney in a fraction of a millisecond so small that no stopwatch ever built could measure it. And this is not a photon or a subatomic particle. This is a mass of iron and neutrons, roughly the size of the Earth, collapsing inward at nearly 1/4 of the speed of light. As the core falls, its temperature soars past 10 billion degrees. At this threshold, the photons flooding the interior carry so much energy that they begin to tear iron nuclei apart, shattering them into helium nuclei and free neutrons, stripping away the products of millions of years of nuclear fusion in a matter of seconds. This is photodisintegration on a grand scale, and it is profoundly destructive. Every iron nucleus that breaks apart absorbs energy from the core, cooling it, reducing its pressure, accelerating the collapse further. The star is dismantling its own skeleton from the inside. Simultaneously, the density is climbing through 1 billion grams per cubic centimeter and beyond, pushing electrons so close to atomic nuclei that they are swallowed whole. Electron after electron merges with a proton, producing a neutron and releasing a neutrino. This is neutronization, the wholesale conversion of the core's matter from atoms into a sea of neutrons. And every electron that vanishes is one fewer source of the degeneracy pressure that was already failing. The collapse is not merely falling now, it is being pulled and pushed and emptied all at once, a runaway process feeding on itself from 3 directions. The neutrinos produced by electron capture stream outward at nearly the speed of light. In the early moments of the collapse, while the density is still below a few 100 billion grams per cubic centimeter, they pass through the core and escape into the body of the star, carrying energy irretrievably into space. The core cannot hold them, it cannot use them. They are gone, and their departure leaves the collapsing core even more bereft of the energy it would need to slow its fall. But as the density continues to rise, past 10 to the 11, 10 to the 12, approaching 10 to the 13 grams per cubic centimeter, something changes. The core becomes so dense that even neutrinos, the most reluctant particles in nature, begin to scatter off the tightly packed neutrons. Their mean free path shortens from thousands of kilometers to a few dozen. They are trapped. For the first time in this star's life, neutrinos cannot escape the core. They are locked inside, and they will remain locked inside until the density drops, which, for the inner core, will not happen for several seconds. This is neutrino trapping, and it marks a turning point. The composition of the core is now fixed. The electron fraction is frozen. Whatever the core is made of at this moment, a dense, neutron-rich soup of heavy nuclei, free neutrons, trapped neutrinos, and residual electrons, that is what it will carry with it to the finish. And the finish is close. The inner core has been falling for roughly 10 milliseconds. In that time, it has collapsed from a sphere roughly the size of the Earth, 6,000 kilometers in radius, to an object roughly the size of a mid-sized city, 50 kilometers across, perhaps 60. The numbers almost resist comprehension. A volume that once held a mass equivalent to our sun, compressed into something you could drive across in less than an hour on a motorway, if there were a motorway, and if the surface gravity were not 200 billion times stronger than the Earth's. The density at the center has reached and surpassed nuclear density, 2.7 times 10 to the 14 grams per cubic centimeter. This is the density of an atomic nucleus itself. The individual neutrons in the core are now so close together that they are essentially touching, and the strong nuclear force, the same force that holds protons and neutrons together inside ordinary atoms, has become repulsive. The neutrons resist further compression. Neutron degeneracy pressure, a quantum mechanical force far more powerful than the electron degeneracy that already failed, rises sharply. The inner core decelerates, slows, stops, and then, like a rubber ball hurled against a concrete wall, it bounces. The rebound is violent and instantaneous. The inner core overshoots its equilibrium radius, compresses past nuclear density, and springs back outward, launching a pressure wave into the still infalling outer core. This wave steepens almost immediately into a shock front, a wall of compressed, superheated matter racing outward at tens of thousands of kilometers per second, slamming into material that is still falling inward at a significant fraction of the speed of light. This is the core bounce. It happens approximately 10 milliseconds after the collapse began. In that 10 milliseconds, the core has gone from a slowly evolving sphere of iron to a proto-neutron star, an object so dense that a teaspoon of its material would outweigh every building in Manhattan, so hot that its temperature exceeds 100 billion degrees, so compact that its surface gravity would crush any known structure into a film of neutrons a few atoms thick. The proto-neutron star is born. The shockwave is launched, and for a brief, furious moment, it looks as though the explosion is already underway, as though the shock will simply tear the star apart and scatter its layers across space. But physics is not finished with this star. The shockwave, powerful as it is, carries only a fraction of the energy released in the collapse. And the material it is ploughing into, the still falling iron of the outer core, is heavy, dense, and cold. Every iron nucleus the shock encounters must be disassembled into free particles, and each disassembly costs energy the shock cannot afford to lose. Within 100 milliseconds, a tenth of a second, the shock has traveled barely 200 kilometers from the center of the star. Its velocity is dropping, its energy is bleeding away. The still infalling matter above it is pressing down like a hand on a flame. The shock stalls. It does not fade entirely. It does not reverse. But it stops expanding, suspended in a precarious equilibrium between the energy driving it outward and the weight of the star pressing it inward. It hovers at a radius of roughly 100 to 200 kilometers from the center, trembling, uncertain, caught between explosion and oblivion. The star has reached the most critical moment of its existence. If the shock revives, the star explodes, a supernova, visible across the universe. If the shock dies, the star collapses silently into a black hole. No explosion, no light, no scattered elements. Just a quiet subtraction from the galaxy's census of living stars. Everything depends on what happens next. For decades, this is where the physics broke down. Simulations of core collapse supernovae run on the most powerful computers available would reach this exact moment. The shock stalled at 100 or 200 kilometers, the star hanging between explosion and silence, and fail. The shock would lose energy, the infalling material would smother it, and the entire star would slide into a black hole without so much as a flash. On paper, massive stars were supposed to explode. In practice, the computers could not make them. This was the supernova problem, and it haunted astrophysics for the better part of 40 years. The universe was clearly producing supernovae. We could see them in distant galaxies. We could measure the elements they scattered. We could photograph the remnants they left behind. But the theoretical models refused to cooperate. Something was missing from the equations, some source of energy or instability that the early simulations could not capture. The stars that were supposed to explode kept collapsing quietly, and the theorists kept staring at their screens, searching for the mechanism that would push the stalled shock back to life. The answer, when it came, arrived from an unlikely direction. It came from the quietest particles in the universe. Hans Bethe and James Wilson proposed the idea in 1985. The concept was elegantly simple, even if the physics behind it was ferociously complex. During the collapse, the newly formed proto-neutron star radiates an enormous flood of neutrinos, roughly 10 to the 58 of them over the course of about 10 seconds, carrying away 99% of the gravitational energy released in the collapse. That energy is staggering, 3 times 10 to the 46 joules, or about 100 times more energy than the Sun will produce in its entire 10 billion year lifetime. All of it compressed into a neutrino burst lasting less than a quarter of a minute. Now, neutrinos are famous for their indifference to matter. 10 trillion of them pass through your body every second, solar neutrinos streaming from the Sun's core, and not one of them will touch a single atom in you during your entire life. A neutrino can travel through a light year of solid lead without being absorbed. Under normal circumstances, they are the closest thing in physics to nothing at all. But the region just above the proto-neutron star is not a normal circumstance. The density there, while far lower than at the core, is still immense by any terrestrial standard. And the neutrino flux pouring out of the proto-neutron star is not a gentle stream. It is a torrent of almost incomprehensible intensity. A wall of particles so dense that even their vanishingly small interaction probability begins to matter. In a zone stretching from about 30 kilometers to roughly 300 kilometers above the center, a region that physicists call the gain layer, a tiny fraction of the outgoing neutrinos are absorbed. They collide with neutrons and protons in the gain layer, depositing their energy as heat. A tiny fraction, perhaps 1% of the total neutrino energy. Under any other circumstances, 1% of anything would be negligible, but 1% of 3 times 10 to the 46 joules is 3 times 10 to the 44 joules, and that is more than enough to unbind the star. The energy needed to blow the outer layers of a massive star into space is roughly 10 to the 44 joules. The neutrinos, by donating the smallest sliver of their colossal energy budget, can do the job. This is the neutrino heating mechanism, and it is the leading explanation for how core collapse supernovae work. But there is a complication, one that kept the models failing for years even after Bethe and Wilson's proposal. In a perfectly spherical star, neutrino heating alone is not quite sufficient. The energy is deposited too slowly, the infalling material drains it too quickly, and the shock does not revive. Something else is needed to break the symmetry and tip the balance. That something arrived in 2003 from a simulation run by John Blondin, Anthony Mezzacapa, and Christine Demarino. Working with a simplified model that deliberately excluded neutrino heating, stripping the problem down to pure hydrodynamics, they discovered that a stalled accretion shock is inherently unstable. Left to itself, the shock does not sit quietly at a fixed radius. It begins to oscillate. It sloshes back and forth, developing large-scale asymmetries, a bulge in one direction, a dent in another, that grow with time. The oscillation is global, dominated by dipole and quadrupole modes, and it has a characteristic period set by the time it takes a pressure wave to travel from the shock down to the proto-neutron star and back. They called it the Standing Accretion Shock Instability, SASI for short, and it changed the field. The mechanism behind SASI is an advective acoustic cycle. Perturbations in entropy and vorticity are carried inward by the accreting matter, falling toward the proto-neutron star. When they reach the dense layers near the surface, they generate acoustic waves, pressure disturbances that propagate outward at the local speed of sound. These acoustic waves slam into the shock from below, deforming it, and the deformed shock produces new entropy and vorticity perturbations that are again advected inward. The cycle repeats, and with each repetition, the amplitude grows. The shock develops a pronounced sloshing motion, sometimes settling into a spiral mode that rotates around the proto-neutron star like water circling a drain. This changes everything for the stalled shock. The large-scale asymmetries push portions of the shock to larger radii, where the infalling material is less dense and easier to heat. Simultaneously, the turbulent convection behind the shock, driven partly by SASI and partly by the negative entropy gradient that neutrino heating creates, forces the accreted material into complex, non-radial trajectories. Instead of falling straight through the gain layer and out the other side, matter lingers. It follows looping, spiraling paths that keep it exposed to the neutrino flux for longer. The dwell time increases, the heating increases, and at some point, 100 milliseconds after bounce in some models, 600 in others, the accumulated energy is enough. The shock expands, it accelerates, it breaks free. The star explodes, not spherically, not symmetrically. The explosion carries the imprint of every instability that helped launch it. One hemisphere may expand faster than the other. Jets of nickel-rich material may punch through the stellar envelope at thousands of kilometers per second, while other regions lag behind. The proto-neutron star itself is kicked in the opposite direction by the asymmetric ejection, sometimes receiving a natal kick of hundreds of kilometers per second, fast enough to eventually escape the galaxy entirely. The sloshing, spiraling chaos of the stalled shock phase is written permanently into the geometry of the explosion, and it is visible, billions of years later, in the lopsided shapes of supernova remnants like Cassiopeia A. But all of this, the asymmetric explosion, the neutron star kick, the scattered elements, begins with a 1% energy donation from particles that barely interact with matter, amplified by an instability that no one predicted until 2 decades ago. The ghost saves the star. The quietest particles in the universe produce the loudest event it knows. And in the moment the shock breaks free, something else escapes. Something that will cross 168,000 light-years of empty space and arrive at a small blue planet called Earth, where it will be caught in underground tanks of water and where it will confirm that everything we think we know about the death of a star is, in its broad outlines, correct. On February the 23rd, 1987, a blue supergiant star in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, roughly 168,000 light-years from Earth, ran out of time. Its iron core crossed the Chandrasekhar limit. The collapse took milliseconds. The bounce launched a shock. The shock stalled, revived, and tore the star apart. And in the first seconds of that catastrophe, before the shock wave had even begun its hours-long journey to the stellar surface, a flood of neutrinos poured out of the newborn proto-neutron star and raced into space at very nearly the speed of light. Those neutrinos traveled for 168,000 years. They crossed the void between the Large Magellanic Cloud and the Milky Way. They entered our galaxy, threaded through its spiral arms, past countless stars and dead worlds and empty reaches of interstellar dust. And on that February morning, they arrived at Earth. Billions of them passed through every square centimeter of the planet's surface. They streamed through the oceans, through the crust, through the mantle, through the iron core at the center of the Earth, and out the other side, continuing into space as though our entire world were made of glass. Almost none of them stopped. Almost none of them touched a single atom. That is what neutrinos do. They pass through matter as if it does not exist. But the key word is almost. Deep underground in a zinc mine in the Japanese Alps, a cylindrical tank called Kamiokande II held 3,000 tons of ultra-pure water, monitored by about 1,000 photomultiplier tubes, sensors so sensitive that they could detect the faint blue flash produced when a single subatomic particle moved through the water faster than light travels in that medium. The detector had been built to search for proton decay, a process predicted by grand unified theories of particle physics. It had not been designed to catch neutrinos from a dying star. But at 7:35 Universal Time on that February morning, 12 of its photomultiplier tubes fired in rapid succession. 12 events, 12 anti-neutrinos from a supernova 168,000 light-years away, captured in a tank of water beneath a mountain in Japan. 6,000 kilometers to the west, under the shore of Lake Erie, in a salt mine near Cleveland, Ohio, a similar detector called IMB, the Irvine, Michigan Brookhaven experiment, recorded 8 more anti-neutrinos in the same 13-second window. And in the Baksan Valley in the Caucasus Mountains of southern Russia, a liquid scintillator detector registered 5 additional events. 24 neutrinos. That was the total harvest from 3 detectors on 3 continents, listening to the death of a star across intergalactic space. 24 out of the roughly 10 billion trillion that passed through the Earth in those 13 seconds. The ratio is so lopsided that it borders on absurdity. It is like dipping a thimble into the Pacific Ocean and pulling out exactly one specific molecule of water. And yet those 24 detections were enough. They were enough to confirm that the theoretical picture of core collapse, the iron crisis, the bounce, the neutrino burst, the energy budget, was, in its essentials, correct. They were enough to establish that 99% of the energy of a supernova is indeed carried by neutrinos, not by light. And they were enough to open an entirely new field of science, neutrino astronomy. The Nobel Prize in Physics followed. The data from Kamiokande II were particularly revealing. The 12 anti-neutrinos did not arrive in a single uniform cluster. They came in 2 distinct pulses. The first pulse, 9 events, arrived within a span of roughly 2 seconds. Then there was a pause. Then 3 more events trickled in over the following 10 seconds. This 2-phase structure matched the theoretical predictions almost exactly. The initial burst corresponded to the accretion phase, when matter was still raining down onto the protoneutron star and the neutrino luminosity was at its peak. The later, quieter phase corresponded to the cooling of the protoneutron star itself as it radiated away its thermal energy over a longer timescale. The optical confirmation came 2 to 3 hours later, when astronomers in Chile and New Zealand independently noticed a new bright point of light in the Large Magellanic Cloud. The delay was precisely what the models predicted. Neutrinos, generated at the moment of core collapse and able to escape the dense interior almost immediately, raced ahead. Light, trapped by the opaque layers of the star, could not escape until the shock wave had ploughed through the entire stellar envelope and broken through the surface. A journey that took hours. The neutrinos were the messenger. The light was the confirmation. The progenitor star was later identified as Sanduleak -69202, and it delivered a surprise of its own. Theorists had expected that the stars most likely to explode as Type II supernovae would be red supergiants, cool, bloated, enormous. Sanduleak -69202 was a blue supergiant, hotter, more compact, and not at all what the textbooks predicted. The discrepancy forced a significant revision of stellar evolution models and remains a subject of active research nearly 4 decades later. But the deeper legacy of SN 1987A is not about one star or one surprise. It is about what 24 particles told us. They told us that the neutrino mechanism works. They told us that the energy budget of a core collapse supernova is overwhelmingly neutrino-dominated. They told us that the timescale of the burst, seconds, not hours or days, is consistent with the rapid cooling of a newly formed neutron star. They placed upper bounds on the mass of the electron neutrino and constrained the number of neutrino species. From 24 events captured in underground water and scintillator, a generation of physicists extracted an astonishing amount of information about the interior of a collapsing star. 24 was enough for 1987. But the next time a massive star dies in our corner of the universe, 24 will not be the number. It will not be close. Because in the decades since that February morning, the world has been building something far larger, far more sensitive, and far more ambitious. Detectors that will catch not dozens, but tens of thousands of neutrinos from the next galactic supernova. And that will read in those particles a level of detail that Kamiokande and IMB could never have dreamed of. The cathedrals are under construction, and they are waiting for a star to die. a mile beneath the Black Hills of South Dakota, in excavated caverns that once held a gold mine, engineers are assembling a detector filled with 40,000 tons of liquid argon, cooled to -186 degrees Celsius. The liquid is so pure that an electron drifting through it can travel several meters without being absorbed, a requirement so exacting that even a few parts per billion of oxygen contamination would ruin the measurement. The detector is called DUNE, the Deep Underground Neutrino Experiment, and when it reaches full operation in the early 2030s, it will be the most sensitive instrument ever built for catching a specific kind of particle, the electron neutrino. This matters because the detectors that caught the neutrinos from SN 1987A, Kamiokande, IMB, Baksan, were primarily sensitive to electron antineutrinos, the antimatter counterpart. They captured the thermal glow of the cooling proto-neutron star, which is dominated by antineutrinos of all flavors. But the very first neutrinos emitted in a core collapse, the sharp, brief spike produced by neutronization when electrons are crushed into protons during the initial milliseconds of the implosion, are pure electron neutrinos. No detector in 1987 could see them. DUNE, with its liquid argon target, can. When an electron neutrino strikes an argon-40 nucleus, it converts it into an excited potassium-40 nucleus and kicks out an electron, leaving a distinctive trail that the detector's sensors can reconstruct in 3 dimensions. For a supernova at the center of the Milky Way, roughly 10 kiloparsecs, or about 33,000 light-years away, DUNE expects to record approximately 2,000 of these interactions. Not 24, 2,000. Half a world away, inside a mountain in the Kamioka region of Japan, a different cathedral is taking shape. Hyper Kamiokande is the successor to the detector that caught those 12 antineutrinos in 1987. Where Kamiokande II held 3,000 tons of water, Hyper Kamiokande will hold 260,000. A cylindrical tank 74 meters wide and 60 meters tall, lined with tens of thousands of photomultiplier tubes of a newer, more sensitive design. Its first tank is scheduled to begin collecting data in 2027, and its target is the same particle that Kamiokande excelled at detecting, the electron antineutrino, captured through inverse beta decay when an antineutrino strikes a proton and produces a positron and a neutron. For a galactic supernova, Hyper Kamiokande expects not hundreds but tens of thousands of antineutrino events in the space of 10 seconds. The 2 experiments are complementary by design. DUNE sees the electron-neutrino channel. Hyper Kamiokande sees the electron antineutrino channel. Together, they can reconstruct the full flavor spectrum of a supernova's neutrino emission, a feat that would give physicists a second-by-second portrait of the proto-neutron star's birth, its thermal evolution, and the dynamics of the shock revival that produces the explosion. If the proto-neutron star collapses further into a black hole, if the shock fails and the remnant swallows itself, the neutrino signal will cut off abruptly, a sharp silence that would be unmistakable in either detector. For the first time, we would witness the formation of a black hole in real time, not by seeing it, but by hearing it go quiet. There is also the matter of warning. Neutrinos escape the collapsing core almost immediately, while light remains trapped inside the star until the shockwave breaks through the surface, a process that takes hours. This gap, neutrinos first, light later, means that a network of neutrino detectors can serve as an early warning system for astronomers. The system already exists. It is called SNEWS, the Supernova Early Warning System, and it links neutrino observatories around the world into a single automated alert network. When multiple detectors register a burst of neutrino events within a narrow time window, SNEWS sends an alert to telescopes worldwide, giving them time to orient toward the source before the first photons arrive. With DUNE and Hyper Kamiokande online, the directional sensitivity of the neutrino data itself will help pinpoint where in the sky the supernova is occurring, a capability that Kamiokande and IMB did not have in 1987. And the neutrinos are not the only signal. The violent asymmetries of the stalled shock phase, the SASI oscillations, the convective plumes, the lopsided launch of the explosion, will produce gravitational waves, ripples in the fabric of space-time that propagate outward at the speed of light. LIGO, Virgo, and CAGRA, the laser interferometers that first detected gravitational waves from merging black holes in 2015, are sensitive enough to detect the gravitational wave signature of a core collapse supernova within our galaxy. The frequency of the SASI oscillation, typically between 80 and several hundred hertz, falls squarely in their detection band. A galactic supernova would give us 3 simultaneous messengers arriving within seconds of each other: neutrinos, gravitational waves, and hours later, light. The last supernova observed in our own galaxy was Kepler's in 1604, over 4 centuries ago, before the invention of the telescope. Observations of the radioactive isotope aluminium-26 produced by massive stars suggest that core collapse supernovae occur in the Milky Way at a rate of roughly 2 per century, give or take. We have been mildly unlucky, but the statistics favor patience. Within the operational lifetime of these next-generation detectors, a galactic supernova is not merely possible, but probable. And when it comes, the data we collect in those 10 seconds of neutrino emission will reshape our understanding of stellar death, neutron star physics, and possibly the fundamental properties of the neutrino itself. This is what we have built in the 39 years since 24 particles flickered in underground water. From a thimble dipped in the ocean, we have constructed reservoirs. From a whisper overheard in a mine shaft, we have designed concert halls. The next time a massive star in the Milky Way reaches the end of its silicon and crosses the Chandrasekhar limit, we will not catch a glimpse. We will watch the whole performance, from the first millisecond of collapse to the last fading glow of the cooling remnant, and we will do it in neutrinos, in gravitational waves, and in light all at once. But we do not need to wait for a galactic supernova to study stellar death. Even now, with existing telescopes, we are watching stars die in nearby galaxies. And one recent explosion, close enough to study in extraordinary detail, has given us a front-row seat to the physics we have spent this documentary describing. On the evening of May the 19th, 2023, a Japanese amateur astronomer named Koichi Itagaki pointed his telescope at Messier 101, the Pinwheel Galaxy, a large spiral galaxy 21 million light-years away in the constellation Ursa Major, and noticed something that had not been there before. A new point of light, magnitude 14.9, sitting along one of the galaxy's outer spiral arms. Within hours, the Zwicky Transient Facility in California confirmed it. Spectra taken shortly afterwards revealed the unmistakable hydrogen lines of a Type II supernova. A massive star, roughly 15 times the mass of our Sun, had just destroyed itself. The supernova was designated SN 2023 IXF, and it became the closest core collapse supernova observed in over a decade. Not close by human standards, 21 million light-years is an unimaginable distance. But by the standards of supernova science, it was practically next door, close enough to study with every major telescope on Earth and in orbit, close enough for backyard astronomers to photograph with equipment no more sophisticated than a 4.5-inch reflector, close enough to generate more than 80 published research papers within 2 years of its discovery. What those papers revealed was a star that had not gone quietly into its final years. The spectra of SN 2023 IXF showed strong signatures of interaction between the supernova ejecta and dense material surrounding the star, circumstellar matter, the residue of powerful mass loss episodes in the final years, perhaps the final months before the explosion. The progenitor had been shedding its outer layers aggressively, coughing up shells of gas and dust into its immediate environment, as though the star were already coming apart before the core collapse finished the job. This kind of pre-explosion mass loss is one of the least understood aspects of massive star evolution. We know it happens, we see the evidence in supernova after supernova, but the mechanism that drives it remains an open question. Something destabilizes these stars in their final stages, and SN 2023 IXF, because of its proximity, offered one of the most detailed views of that process yet recorded. NASA's Fermi Gamma Ray Space Telescope watched the event for a full month after discovery and detected no gamma rays, a result that surprised many researchers. Supernovae had long been suspected of accelerating cosmic rays, the high-energy particles that constantly bombard the Earth from all directions, and gamma rays produced by those cosmic rays interacting with surrounding material were expected to be detectable from a supernova this close. The upper limit from Fermi's observations placed the energy conversion into cosmic ray acceleration at roughly 1%, far below the 10% that earlier estimates had assumed. It did not rule supernovae out as cosmic ray factories, but it narrowed the margin considerably. These are the kinds of details that only a nearby supernova can provide. Most of the thousands of supernovae discovered each year are so distant that they appear as little more than points of light superimposed on the glow of their host galaxies. SN 2023 IXF was different. It was close enough for its progenitor to be identified in archival images, close enough for the circumstellar interaction to be studied spectroscopically night after night, close enough for the asymmetry of the explosion to be measured through spectropolarimetry. It was, for the supernova community, a gift. But there is a star much closer than anything in the Pinwheel Galaxy, a star that anyone with functioning eyesight can find on a clear winter night, that will, one day, do the same thing. And its name is the most famous in the sky: Betelgeuse, Alpha Orionis, the left shoulder of the Hunter, a red supergiant roughly 650 light-years from Earth. Not 650 million, not 650,000, but 650. Burning with 100,000 times the luminosity of the Sun, its surface so distended that if it replaced our star, it would engulf everything out to the orbit of Mars. It is one of the 10 brightest stars visible from Earth, and it is dying. We know it is dying because of what it is. Red supergiants are the final evolutionary stage of massive stars before core collapse. Betelgeuse has already exhausted the hydrogen in its core, likely the helium as well, and is almost certainly burning heavier elements in the concentric shells we described earlier in this documentary. It is somewhere on that accelerating staircase of nuclear fuels, though precisely which step it currently occupies is a matter of active and occasionally heated debate. In late 2019, Betelgeuse did something alarming. Over the course of a few weeks, its brightness dropped by roughly 40%, plunging from one of the top 10 brightest stars in the sky to outside the top 20. The dimming was dramatic enough to be visible to the naked eye, and it set off a wave of speculation in both the scientific literature and the popular press that the star might be on the verge of exploding. Headlines asked whether Betelgeuse was about to go supernova. Social media was, briefly, consumed by the prospect. It was not. The cause of the great dimming, as it came to be known, turned out to be far more mundane. A massive cloud of dust, ejected from the star's turbulent surface, had drifted into our line of sight and partially obscured the star. When the dust dispersed, Betelgeuse returned to its usual brightness. The star was not dying any faster than it had been the week before. It had simply sneezed. But the story did not end there. Betelgeuse has long been known to vary in brightness on two timescales: a shorter cycle of about 400 days, attributed to pulsations in the star's outer layers, and a longer cycle of roughly 2,100 days, or about 6 years, whose origin had never been satisfactorily explained. In July of 2025, a team led by Steve Howell at NASA's Ames Research Center announced that they had directly imaged, for the first time, a stellar companion orbiting Betelgeuse, a smaller star, roughly 1.5 times the mass of the Sun, tucked so close to the red supergiant that it orbits within the giant's extended atmosphere. The companion was given the name Siwarha, an Arabic word meaning her bracelet, echoing the Arabic roots of Betelgeuse's own name. The International Astronomical Union formally recognized the name in September of that year. Siwarha changes the picture considerably. If the 6-year brightness cycle is caused by the companion's orbital influence, stirring dust, redistributing material in Betelgeuse's atmosphere, then it is not an intrinsic property of the star's internal evolution. And that distinction matters for the question everyone wants answered. When will Betelgeuse explode? If the long cycle were intrinsic, some models placed the star in a very late evolutionary stage, potentially only decades from collapse. With Siwarha in the picture, those models no longer apply. Current estimates have returned to a more conservative timescale. Betelgeuse will almost certainly explode, but probably not for another 100,000 years or more. When it does, the show will be worth the wait. A Betelgeuse supernova would peak at an apparent magnitude somewhere between -8 and -12, easily visible in daylight, possibly approaching the brightness of the full moon, though concentrated in a single searing point rather than spread across a disk. You could read by its light at midnight. It would remain visible for 2 to 3 months before fading, and at 650 light-years, it poses no danger whatsoever to life on Earth. We would need to be within about 160 light-years for a supernova to do real biological harm, and Betelgeuse is 4 times that distance. Somewhere, deep inside that orange-red point of light in Orion's shoulder, shells of heavy elements are nested one inside the other, and a core of iron or something close to it is growing. The silicon clock may already be running, or it may not start for 100 millennia. We do not know. What we do know is that the physics is the same. The Chandrasekhar limit is the same. The collapse, the bounce, the stalled shock, the neutrino flood, all of it will happen exactly as we have described when the time comes. And the next supernova to reach our instruments will not necessarily be Betelgeuse. It could be any one of the hundreds of massive stars scattered through the Milky Way's spiral arms, most of them too faint or too obscured by dust for us to monitor. The star that gives us our next galactic neutrino burst may be one we have never heard of, a red supergiant buried behind a curtain of interstellar dust in the far reaches of the galaxy, invisible to optical telescopes, but perfectly visible to the neutrino cathedrals waiting underground. Whatever star it is, and whenever it happens, we now know what it will look like from the inside. We know what happens when the silicon runs out and the iron core crosses the line. We know about the collapse, the bounce, the stall, and the ghost that pushes the shock back to life. We have followed this process from beginning to end, in theory, in simulation, and in the 24 particles that flickered in underground water on a February morning in 1987. But there is one part of the story we have not yet told. The explosion does not merely destroy, it creates. And what it creates in a single second of nuclear fire is the raw material for everything that comes after. The shockwave tears through the silicon shell at tens of thousands of kilometers per second, and as it passes, something remarkable happens. The temperature behind the front spikes by roughly 50%, soaring into the billions of degrees. And in that brief, searing passage, nuclear reactions ignite with a fury that dwarfs anything the star produced during its lifetime. This is explosive nucleosynthesis. It lasts approximately 1 second, and in that 1 second, the shockwave forges more varieties of atomic nuclei than the star created in the previous 10 million years. The process works differently depending on which layer the shock is passing through. In the silicon and oxygen shells, closest to the collapsed core, the temperatures are high enough to drive matter into nuclear statistical equilibrium, the same state that governed the final hours of silicon burning. Nuclei are broken apart and reassembled at a frantic rate, and the products settle overwhelmingly into the iron group: nickel, cobalt, iron, and their neighbors on the periodic table. The dominant product is nickel-56, the same isotope that silicon burning created in the core. But now it is being produced in quantities vastly larger than anything the core generated, because the shockwave is processing entire solar masses of material in moments rather than days. Nickel-56 is unstable. It decays, first into cobalt-56 with a half-life of about 6 days, and then into stable iron-56 with a half-life of 77 days. This two-step decay chain is not a minor footnote. It is the engine that powers a supernova's visible light. The energy released by the radioactive decay of nickel and cobalt heats the expanding debris cloud from within, and as the ejecta thin out and become increasingly transparent over the following weeks, that heat escapes as the light we observe through our telescopes. When astronomers plot a supernova's brightness over time, its light curve, the shape of that curve is largely dictated by the mass of nickel-56 produced in the explosion and the rate at which the ejecta become transparent. The supernova we see is, in a very direct sense, powered by nuclear decay. Farther out, in the oxygen, carbon, and helium shells, the shockwave drives a different kind of nucleosynthesis. The temperatures are lower, the equilibrium conditions less extreme, and the products are lighter: silicon, sulfur, argon, calcium, titanium. These are the intermediate mass elements, and they are produced in abundance. The recent three-dimensional simulations by David Vartanian and collaborators, the first to follow a supernova from core bounce all the way through shock breakout, published in 2025, showed that nickel-rich ejecta from the deepest layers can travel at velocities as high as 7,000 kilometers per second, closely trailing the forward shock. The explosion is not a uniform expansion. It is lumpy, asymmetric, riddled with fingers of heavy material punching through lighter layers and mixing elements that the star had kept neatly separated for millions of years. There is also a process occurring in those first seconds that operates on a timescale almost too fast to follow. In the neutron-rich material closest to the proto-neutron star, free neutrons are extraordinarily abundant. Atomic nuclei immersed in this flood of neutrons capture them at a rate faster than the nuclei can radioactively decay, a regime called the rapid neutron capture process, usually shortened to R process. In this environment, nuclei climb the neutron-rich side of the chart of Nucleides in a matter of seconds, building isotopes so heavy and so unstable that they exist only fleetingly before cascading through chains of beta decay into more stable forms. The R process is responsible for roughly half of all elements heavier than iron in the universe: gold, platinum, uranium, thorium, the rare earth elements that make modern electronics possible. For decades, core collapse supernovae were considered the primary site of the R process. That picture has grown more complicated in recent years. The detection of gravitational waves from a neutron star merger in 2017, an event called GW170817, and the subsequent observation of a kilonova rich in R process elements demonstrated that neutron star collisions are also prolific producers of heavy elements and may in fact be the dominant source. The relative contributions of supernovae and mergers remain one of the most actively debated questions in nuclear astrophysics. What is not in dispute is that both mechanisms exist, and that the heavy elements in your environment, the gold in a ring, the uranium in a reactor, the neodymium in a speaker magnet, were assembled under conditions of almost inconceivable violence, either in the seconds following a core bounce or in the collision of two city-sized objects at a third of the speed of light. When the shock wave finally breaks through the hydrogen envelope and the star's outer surface, hours after the core collapse, the explosion becomes visible. The ejecta are expanding at thousands of kilometers per second, carrying with them the stratified products of 10 million years of nuclear evolution and 1 second of explosive reprocessing, all jumbled together by the turbulence and instabilities of the blast. Behind them at the center, something remains. If the original star was below a certain mass threshold, roughly 20 to 25 solar masses at birth, though the exact number depends on factors including metallicity, rotation, and the details of the explosion, the remnant is a neutron star. It is roughly 20 kilometers across, rotating rapidly due to the conservation of angular momentum. The same principle that makes a spinning figure skater speed up when they pull their arms inward, except here the contraction is from an object the size of the Earth to an object the size of a borough. The surface gravity is 200 billion times that of the Earth. The magnetic field, compressed and amplified during the collapse, can reach 1 trillion times the strength of the Earth's. If the neutron star's magnetic axis is misaligned with its rotation axis, it sweeps beams of radiation across space like a lighthouse, and we detect it as a pulsar, a rapidly pulsing source of radio waves, sometimes also X-rays and gamma rays, spinning anywhere from once every few seconds to hundreds of times per second. If the progenitor was more massive, or if enough material falls back onto the proto-neutron star after the initial explosion, the remnant exceeds the maximum mass that neutron degeneracy pressure can support, and it collapses further. There is no next line of defense, no stronger degeneracy pressure waiting in the wings. The remnant passes through its own event horizon and becomes a stellar mass black hole, typically between 3 and perhaps 15 or 20 solar masses. The information about what it once was, the composition, the temperature, the structure, is locked away behind the horizon, inaccessible to the outside universe. Either way, neutron star or black hole, what is left behind is extraordinarily small compared to what came before. A star that once filled a volume larger than the inner solar system has been reduced to an object you could comfortably fit inside a single city. The rest, the hydrogen, the helium, the carbon, the oxygen, the silicon, the nickel, the gold, the uranium, has been returned to the galaxy. It will drift through interstellar space for millions of years, mixing with existing gas and dust, enriching the raw material from which future stars and planets will form. Some of it will find its way into a collapsing molecular cloud. Some of that cloud will become a new star. Some of the leftover material will coalesce into rocky planets, and on one of those planets, billions of years from now, some of those atoms, forged in a core collapse that lasted 10 minutes and scattered by a shock wave that almost failed, may find themselves inside something alive. That is the cycle. And tonight, as this documentary draws toward its close, it is worth pausing to consider what it means. We have come a long way tonight, from the outermost shell of hydrogen to the innermost core of iron, from the slow accumulation of 10 million years to the 10 millisecond freefall that ends them, from a stalled shock, trembling between explosion and silence, to the ghostly particles that push it back to life, From 24 neutrinos caught in underground water to the cathedrals of argon and ultra-pure water being prepared for the next signal. From the distant light of a supernova in the Pinwheel Galaxy to the familiar orange glow of Betelgeuse in Orion's shoulder. From the forge, 1 second of nuclear fire, to the gold and iron and calcium drifting through interstellar space, waiting to become something new. This is the full arc of what happens when a massive star dies. And the fact that we know it at all is, in its own quiet way, one of the more remarkable things our species has accomplished. Consider the difficulty. The event we have been describing takes place inside a star, buried beneath hundreds of millions of kilometers of opaque plasma. No telescope can see it. No probe can survive it. The temperatures are billions of degrees. The densities are beyond anything reproducible in any laboratory on Earth. The timescale, milliseconds for the collapse, seconds for the neutrino burst, hours before light escapes, is too fast for direct observation, too slow for simple experiments, and too complex for any single equation to capture. The physics spans nuclear forces, general relativity, quantum mechanics, fluid dynamics, and neutrino transport, all operating simultaneously in 3 dimensions with no symmetry to simplify the mathematics. For 40 years, the best simulations in the world could not make a star explode. And yet, we pieced it together. Not from a single observation or a single theory, but from decades of work by thousands of people. The spectroscopists who classified supernovae, the nuclear physicists who measured the binding energies, the theorists who proposed the neutrino mechanism and waited 2 decades for the computers to catch up, the engineers who built Kamiokande and filled it with water so pure it was invisible to light, and the graduate student in Japan who, on a February morning in 1987, noticed that 12 of his photomultiplier tubes had fired within 13 seconds. That student's name was Masatoshi Koshiba's team member Kenji Hirata. The data he helped collect earned Koshiba the Nobel Prize in 2002. The 24 neutrinos that Hirata and his colleagues recorded, across 3 detectors, 3 continents, 13 seconds, remain to this day the only direct observational evidence we have of what happens inside a collapsing stellar core. The simulations have advanced enormously since then. Hans Thomas Janker, in a comprehensive review published in 2025, described the past decade of 3-dimensional supernova modeling as a period of tremendous progress. Self-consistent simulations can now follow the entire evolution from core collapse through shock revival, shock breakout at the stellar surface, and the electromagnetic supernova outburst, reproducing observed explosion energies, neutron star kick velocities, and the yields of diagnostic radioactive isotopes. Vartanian and collaborators, using the Fornax code developed by Adam Burrows at Princeton, published the first 3-dimensional simulation to track a supernova from core bounce to beyond shock breakout, a span of over 5 days, showing that the early asymmetry of the explosion is preserved all the way to the moment the shock rips through the star's surface. And in the same year, Kanji Mori and colleagues demonstrated for the first time that neutrino flavor oscillations, incorporated into 3-dimensional models, could significantly enhance the explosion energy, suggesting that even the fundamental quantum behavior of the neutrino may play a role in determining whether a star lives or dies. There are still questions. There will always be questions. We do not fully understand which stars explode and which ones collapse silently into black holes. We do not know the precise boundary between a star that produces a neutron star and one that produces a black hole. The relative contributions of supernovae and neutron star mergers to the production of the heaviest elements remain contested. The role of magnetic fields, stellar rotation, and binary interactions in shaping the explosion is only beginning to be explored in 3 dimensions. The supernova problem, how the stalled shock revives, has been largely solved, but not completely. edge cases remain. Surprises are still possible. But the broad picture holds. A massive star builds an onion of layered elements. The core fills with iron. The iron exceeds the Chandrasekhar limit. The core collapses in milliseconds. The bounce launches a shock. The shock stalls. Neutrinos, amplified by turbulence and instability, push it back to life. The star explodes. The elements are scattered. A neutron star or black hole remains. And the debris, enriched with the products of 10 million years of fusion and 1 second of explosive nuclear synthesis, drifts into the galaxy to seed the next generation of stars and worlds. That is the story. And now, as the night deepens around you, there is one more thing worth sitting with. There is something extraordinary about the fact that the most destructive event a star can undergo is also the event that makes complex matter possible. Without supernovae, the universe would contain only hydrogen, helium, and trace amounts of lithium, the elements produced in the first few minutes after the Big Bang. There would be no carbon, no oxygen, no silicon, no iron, no gold, no calcium, no phosphorus, no DNA, no bones, no blood, no thought. The periodic table beyond lithium is, almost in its entirety, a product of stellar lives and stellar deaths, and the most prolific contributors are the deaths, the core collapses, the explosive nuclear synthesis, the R process cascades that build gold and uranium in a matter of seconds. You exist because stars died. That sentence has been repeated so often that it risks sounding like a platitude, but the physics behind it is specific and astonishing. The iron in your hemoglobin was forged in a core that collapsed at 1/4 of the speed of light. The calcium that gives your bones their strength was manufactured in an oxygen shell that a shockwave processed in less than a second. The phosphorus in your DNA, every strand, every cell, every instruction your body follows to sustain itself, was assembled under conditions so extreme that no facility on Earth can reproduce them. You are not merely made of the stuff of stars, you are made of the stuff of their most violent moments. And there is something else, something harder to articulate, but worth trying. The universe existed for 9 billion years before the Earth formed. For most of that time, matter was simple. Hydrogen drifted through expanding space. Stars formed, burned, and died, each generation enriching the interstellar medium with heavier elements. It was a long, slow process, billions of years of stellar chemistry, billions of supernovae, each one adding a thin layer of complexity to the raw material of the cosmos. And then, 4.5 billion years ago, in a particular corner of a particular spiral arm, a cloud of gas and dust that had been enriched by generations of stellar deaths collapsed under its own gravity. A new star formed at the center. Rocky planets coalesced from the debris. And on the third of those planets, the elements that supernovae had scattered, carbon, nitrogen, oxygen, phosphorus, sulfur, iron, found their way into molecular configurations of such intricacy that they began to copy themselves. Life. It took the universe 9 billion years to make the Earth, and another 4.5 billion years for the matter on that Earth to become aware of itself. And now, in the last few centuries, the last few microseconds of cosmic time, that matter has looked back at the process that created it and understood. Not completely, not perfectly, but in broad strokes, with increasing precision, we have reconstructed the chain of events that begins with a silicon clock ticking toward zero and ends with the atoms in your body. The universe built you from the wreckage of stars, and you, this improbable temporary arrangement of ancient elements, have figured out how it was done. Let that settle. The stars are still burning tonight. Somewhere in the Milky Way, right now, a silicon shell is feeding iron onto a growing core. Somewhere, an iron core is approaching a limit it will not survive. Somewhere a shockwave is stalling, and a flood of neutrinos is building in the heart of a proto-neutron star, preparing to push it back to life. You do not need to think about any of that. The universe will take care of its own machinery, as it has done for 13.8 billion years, and it will keep doing so long after you and everyone you know has returned to the dust that stars once made. For now, rest. Let the night carry you. Let the distant light of Orion, Betelgeuse still burning, still glowing its familiar orange-red, be the last thing you picture before you close your eyes. The cosmos is patient. It will still be here in the morning. Sleep well. Good night.